Okay, colleagues, greetings. Hopefully we're live. So today we're going to continue our discussion of the fundamental philosophy of physics. Now, regarding the schedule, I'm doing this, in spare time, provided that I have enough energy. So this is basically, it's, we don't have any schedule. So we'll see. Well, I'm going to see how it goes. I really enjoyed recording yesterday, and this stimulates my mind in all sorts of ways. So again, this is informal. There's no preparation involved on my part. I'm gonna, in many ways, I'm preparing to organize this material in a more structured fashion starting in September. So this is like a work in progress draft. You can, like, open heart surgery. You can see my thought in action. So as a matter of fact, I wanted to get to quantum mechanics as fast as possible, as we were discussing last time. Well, I mean, not just quantum mechanics. I wanted to get to philosophy of physics proper. But it's an interesting fact about me trying to explain philosophy. It's like philosophy of science especially. I always have to begin with a methodological forward. I have to talk about skepticism, right? So we're going to give a very ambitious picture. I'm going to be giving a very ambitious picture, starting, in a couple moments, hopefully, about the Big Bang and the standard model of particle physics. And it's important to understand that this picture does not have a solid foundation. Right, that this is our best hypotheses, and it's a weird situation because on the one hand, methodologically speaking, it's not grounded on anything, and it could, like in principle, in theory, if you want to imagine it, it could turn out to be all completely wrong, and it all could break down in the next moment. So there's absolutely no guarantee that this will continue to hold into the future. But on the other hand, I feel it is by far the best account that we are able to give, and basically every decision I make throughout the day, and decisions that you make throughout the day, again, I have my glass of water with llamas this time. I take a sip, imagining that this is not going to poison me, and the best justification of that I have is science. So it's science is at the same time radically uncertain, and also we have to rely on it completely. So there's this interesting dichotomy between complete uncertainty and complete certainty, because as I take a sip, it doesn't even cross my mind that, maybe the Higgs field is in the false vacuum and I'm going to die in the next moment. Or for some reason, let's say this water will turn to poison and will destroy me. Again, Sextus Empiricus talks about this. Acquiescing before the appearances. The appearances force themselves upon us, but, science doesn't really go below the appearances. But on the other hand, again, it is by far the best instrument that we have, and people who imagine that somehow, religion offers a more secure foundation, I think are just dead wrong. Even, I feel that this is a very important issue, in the sense that, very often people will say, well, science only gets you so far, but then there are important questions in life about the meaning of life, about goodness and what you should do, normative questions, and these questions can never be answered by science, and we need something else, let's say religion, in order to do that. And I deeply, deeply disagree with that point. I need to get to this. So we talked a little bit about the is-ought problem last time, and it's very clear that you cannot derive normative statements from positive statements. So in this straightforward sense, science cannot tell you what is right. Again, Hobbes has this insight. One person plants flowers, another person eats children. We are all chaotic matter in motion. Whatsoever is the object of any man's appetite or desire, that is it which he calls good, and the object of his hate and aversion evil. There being nothing simply and absolutely so. However, it is also true that human beings are not, we're not gods. We cannot just, it's like, let's say I'm thirsty, I cannot choose to not be thirsty. I find myself in a body. There is a human nature, right? And this, so it's not science that tells you what is right and wrong. It is your nature, your passions that tell you what you want, right? And you can try to fight against your passions, and you can be maybe successful to some extent, but you can never be completely successful in that. And at the end of the day, I feel that you can choose which passions to affirm, and again, like John Stuart Mill will talk about higher and lower pleasures, or Michel Foucault will talk about, again, techniques of the self, hermeneutics of the self, techniques of the self. But it's, you're choosing one set of desires over another set of desires. You cannot just, stand outside of this world and, just sui generis, do whatever, be completely free and undetermined. And so, all sorts of reasons to talk about quantum mechanics and cosmology, but this is our fundamental understanding of the world around, right? And it has ethical implications, because if the scientific story is true, and we have this standard model of particle physics. By the way, I realized this morning that this equation is actually wrong. This equation is wrong because it does not include gravity. Okay? So, by the way, physicists in the room, feel free to chime in. If I'm making mistakes in terms of physics, by all means, feel free to correct me. So anyway, but if not this, we have a different equation. Frank Wilczek calls it the core theory, the equation of the core theory, and I could show it to you. Well, this is Sean Carroll's rendition of the equation. So this is the core theory equation. It needs to be expanded, but that's the basic idea. So this is actually the correct equation, and this one is only a part of this equation. It's not complete. It doesn't include gravity. Anyway, so what I'm driving at is that if this description of reality is actually true, although we cannot know this, and it's important to understand, but this is our best guess, this has ethical implications. This has implications for what constitutes the meaning of life and what constitutes you, right? And if you've heard my courses on moral philosophy or political philosophy, you know where my sympathies lie. We start with Hobbes, we go through Rousseau and Mill to Marx and Nietzsche. But I feel that all of these, and from Nietzsche you can go to Lacan and to Foucault. But I feel that all of these insights, all of the insights that these philosophers are giving, they're all compatible and they all hang together on something like this picture. So I'm pointing. No, yeah, in this direction. Yeah, in this direction. I'm pointing in this direction, in the direction of the equation. And for me, one of the most liberating experiences in my life was reading Jacques Lacan, because this is what Lacan does. So it's not any particular statement that he makes, but just in general, this method of looking at a human being as a physical system, if you want, as a deterministic system predetermined, by laws of energy transfer within the psyche, and reading this kind of methodology was deeply liberating for me, and so like Lacan and Buddhism and quantum mechanics, they all hang together, I feel, in an important sense. And this is what I'm trying to share in these talks. Anyway, let's go to work, because I talk too much about extraneous stuff. I want to get to physics. So, what is the basis of our modern understanding? So, physics is actually simple. Physics is simple. You would be surprised to know. It's you would imagine. In fact, physics is the simplest thing to understand. And in fact, we understand physics quite well, as far as we can tell, right? And immediately people will say, well, but if everything is made of physics and you understand physics, then surely you would understand everything. And you see, this is the problem. It doesn't work that way. This has to do with complexity and reductionism. So what I'm trying to say is that you can have a very simple physical system. Let's make a toy model. Three-body problem. So let's take just Newtonian mechanics, nothing fancy, not even Einstein. We take Newtonian mechanics, and we just take three bodies, three objects with mass, and we want to calculate their trajectories. Like, how are they going to behave? There's mutual gravity between the three bodies, right? And as they move, right, this system dynamically changes to accommodate their motion. And it turns out that only certain special configurations of the three-body problem can be solved exactly. And there is, to this day, my mathematician friends tell me that you shouldn't bet on it. Like we're not gonna be able to solve the three-body problem. So, my philosopher friends tell me, well, you should never jump to conclusions. Maybe tomorrow we'll solve it. Well, I wouldn't count on it. Right? But it's impossible to prove a negative. But so far as we can tell, the three-body problem has no exact algebraic solutions, I guess. It has to do with us being unable to solve differential equations exactly. Like you can brute force the approximate solution, but the problem is that the three-body system in a generic configuration is chaotic, and because it's chaotic, the brute force method gives you errors, and these errors and imprecisions, they stack such that, basically the notion is that the system becomes, for you, effectively unpredictable. So in a generic case, even though it's a very simple system that is governed by very simple rules, again, the equation is extremely simple. The force between the objects is equal to m1 multiplied by m2 multiplied by the constant g divided by r squared. Right? It's a simple formula, but once you try to expand this to three bodies, so each of because the force is between the two bodies, and now you have three bodies, and you do this dynamically, right? So you have to solve a differential equation, and once you try to do this, this equation has no simple solutions for a generic case. It has solutions. I don't want to get into the weeds. So a simple formula gives rise to extraordinarily difficult behavior, and Stephen Wolfram calls this computational irreducibility. I'm not sure if Wolfram coined this phrase, so let's not credit. But I've heard this phrase recently from Wolfram, and the notion is that some algorithms or programs, and you can think of the three-body problem. When we model it, you can think of it as a kind of a program, I guess. For certain programs, you can look at the program, you can look at the code, and you can say, I know what the answer is going to be. I can take a shortcut, and I can give you the answer. But for many programs, in fact, Wolfram says for most programs, it's not like that. For a generic computer program, the fastest way to know what the outcome of the program is going to be is to let the program run. So in a generic case, for the three-body problem, the simplest solution to the three-body problem is just to let the three bodies interact in physical space, and you will see what the result is. But there's no generic calculation that will allow you to speed this process up. So this is irreducible complexity. So what this means is you can understand physics perfectly well, the basic laws of physics, you can understand them perfectly well, and still not be able to calculate the result of a chemical process, because it's just computationally, exponentially far too complex. So let me just write, well, again, you understand physics, chemistry, biology, and in this sense, again, physics is by far the easiest, even though it underlines. I mean, chemistry just is applied physics, and biology is applied chemistry, so biology is like doubly applied physics. But these levels of complexity stack. So this, again, has to do with complexity reductionism. The word that gets thrown around is emergence, that you get, and well, this strong emergence, weak emergence, I mean weak emergence. That yes, the system is technically reducible, theoretically it's reducible, but in practice, in terms of your computational ability, it's not. It's effectively irreducible. So this is weak emergence. Strong emergence says that, as far as we can tell, strong emergence is wrong. Strong emergence is probably false. I say probably because who knows. But what I'm saying is that we have never done an experiment where chemistry does something which violates physics. We have never done an experiment in which biology does something, or neuroscience does something, and it violates physics. There has never been an experiment like this, right? And I feel it's very important to keep in mind. It's like when physicists do experiments, they have to control for all sorts of things. You have the weak interactions, strong interactions, Higgs mechanism, but you never have to control for what kinds of thoughts the physicist has, like whether the physicist is grumpy or sad or in love. Like, anyway, I could talk about all sorts of things for a long time. Maybe I'll come back to this point, but let me continue somewhere. So the basics of our understanding is We have the concordance cosmology, which is called the Lambda-CDM model, and we have the standard model of particle physics. So Lambda-CDM plus the standard model of particle physics. And this is our basic understanding of the entire underpinning laws of the universe. And I'm going to try to spend some time explaining this, at least in some basic outline. So let me say something. I am not a physicist, but I feel that there's maybe a certain advantage to that. So I'm not trying to explain the weeds to you, like how do you take this equation, how do you solve it. You're not here for that, right? We're doing something different. We want to see what are the methodological principles. We want to focus on the big questions and answer the big questions. And I feel that physicists, they understand the weeds much better. Again, I made a mistake. This is the Lagrangian of the standard model. It doesn't include gravity. And there you have it on my slide. So gravity is here in the Lambda-CDM. And the standard model does not include gravity so far. This far. And it's a mistake that I have missed. But I hopefully what I'm trying, the purpose of these kinds of lectures or talks is to focus on the methodological insights and try to explain the methodological insights, and also to say certain things which I feel physicists usually gloss over, to explain them clearly. So we have the Big Bang, right? And the Big Bang is this theoretical event that has taken place. Maybe physicists keep updating, but I feel that it's probably 13.7 billion years ago. You see, perceptive students might ask, well, but we know from Einstein that time is relative. And this is the kind of thing that I feel a physicist would not talk about, but a philosopher would. Yeah. So because Einstein says time is relative, so there are different ways, different modes of keeping time, but there is a natural natural reference frame to use. Let's say you take the rest frame of the cosmic microwave background. So with respect to the rest frame of the cosmic microwave background, the age of the universe is 13.7 billion years, right? But if you take different rest frames, or different frames of reference, you can get a different number, because time is relative. But on the other hand, see, theory of relativity is to some extent about relativity, but it's also about, to some extent, about absolutes, because there's a way to transform. I think it's Lorentz transformation, right? So there's a way to transform one time frame into another time frame. So it's not like anything goes. It's like if a particle is moving close to the speed of light, the age of the universe would be, the way that it would count moments would be different. But there's a strict mathematical way in which you transform from one to the other. Anyway, so rest frame of the CMB. Right, and you could ask, what is our evidence for believing in the Big Bang story? And it's a very interesting question. And I probably if I had like an infinite free time, I'd maybe do a different pass on it, and or maybe I could recommend some videos by physicists who explain this better than I do. But the point is that we have a whole battery of evidence from which we deduce this notion of the Big Bang. And the simplest one is that this was first discovered by I think by Edwin Hubble around the middle of the 20th century, and then was refined quite recently in recent decades. The idea that the universe is actually expanding. The universe is expanding. And this is actually where lambda comes from. Lambda is the cosmological constant. Lambda is the rate of expansion of the universe. Or maybe it's our best guess right now what lambda is. Lambda is the vacuum energy that pushes space apart. So actually, lambda is dark matter. For those of you who know. Lambda is dark matter. sorry, dark energy. I'm sorry, I'm deeply sorry. Dark energy. Lambda is dark energy. Well, Lambda-CDM, lambda stands for dark energy, and CDM stands for cold dark matter. We're not sure if it's true, but it's our best guess. And the idea is that if you see immediately. This is why I'm doing this. I told you it's a low effort. I'm doing this live because lambda actually acceleration. It's an interesting issue because the universe doesn't just expand, but it expands at an increasing rate. The universe is expanding, and the rate of the expansion of the universe is increasing. And Edwin Hubble didn't know that. So the Big Bang model, it doesn't matter. In the beginning, the Big Bang model was just, we see the universe expanding, and so let's rewind the clock. It's a very simple procedure. And I feel you have every right to be skeptical of this procedure. How do you know if you can just rewind the clock? So in your head, you do a thought experiment, you rewind the clock, and you say, if all the galaxies are moving away from each other, then we would, if we would extrapolate this into the past, we would imagine that all the galaxies had to have been closer together in the past, right? And this, by doing this thought experiment, you get to the point that, in the past, the universe was much denser and much hotter. Now, immediately, let me say something. What happens at time t equals 0? And this is a pet peeve of mine. This is why I do not trust physicists to talk about the philosophy of the Big Bang. Because many physicists will tell you what happens at the moment of the Big Bang. Or they will say, oh, time did not exist at t equals to 0. Or maybe, let's say, time did not exist before t equals 0 in their model. But what they forget, what good physicists will tell you, is that actually what happens at time equals 0, our models break down. Well, technically speaking, our models break down even earlier. Probably there's as you rewind back, you get to the so-called Planck scale, and Planck scale is where gravity is super important, but also quantum mechanical effects become important. So at Planck scale, we need quantum gravity. And so once you get to the Planck scale, all bets are off. We do not understand the Planck scale. Much less do we understand things that happened before the Planck scale. I could look up the Planck scale, but it's maybe it's a zeptosecond. Who knows? Zeptosecond after the Big Bang. So it's not t equals 0, but it's t equal to 10 to the minus 23 or something. Don't quote me on this, okay? Quantum effects come into play, and all bets are off. So again, the point is that we do not know, and it's illegitimate to extrapolate our models before the Planck scale kicks in. And it's also definitely much more so. It's illegitimate to extrapolate our models to t equals 0 within this, again, so t equals minus 13.7 billion years ago. Because what happens is that you divide by 0 when you get there. And we do not know what happens when you divide by 0, okay? So for the same reason, we do not know what happens inside of black holes. The singularity, in principle, in theory, is supposed to be the point of infinite density. But again, you are dividing by 0 at the center of the black hole. So strictly speaking, you should say, my model does not predict what's going to happen there. Who knows? Maybe there's some interesting quantum transitions or different kinds of matter. Who knows? Different states of matter or different states of energy. We do not know, okay? And I suppose immediately you could ask, and this is why I don't want to get bogged down in the weeds, and again, a physicist would explain this better, but as a philosopher, well, again, I want to say we have huge array of evidence for the Big Bang. So there's this expansion. In fact, we have expansion which speeding up expansion of the universe. But there's also the cosmic microwave background, the CMB. And you can look on the CMB, cosmic microwave background, and you can see all sorts of interesting things. There's called baryonic acoustic oscillations. We can project how the universe, when it was much younger. By the way, whenever I say universe, I mean observable universe, right? So it's kind of important, right? So we're not talking about the beginning of everything that exists, right? We are talking about our observable patch. And what happens outside of our observable universe, or what happened before 13.7 billion years ago, we do not know, because our models break down. So the technical answers we do not know, and there are versions, there are possibilities, and we're going to talk about these possibilities in a moment. So you have this baryonic acoustic oscillation. So when our observable universe was much younger, much smaller, you had these like after the Big Bang, you had these the universe like it rang like a bell. I hope that this analogy is not too misleading. So you had these like waves going in and out, and we can actually see the remnants of these waves in the cosmic microwave background. So it's like if you drop a stone in a pond and there are ripples, there are waves going from that spot. Like in theory, if your lake or something, if your pond was very big and very smooth, you could see the ripples continuing on maybe a year after you have dropped the stone. So a similar thing happens here. We see the ripples in the cosmic microwave background 13.7 billion years after the stone was dropped. And from this we can, it's not just, oh, the Big Bang happened, right? There are equations, there are predictions, there are specific models with specific mathematical parameters. There's also another thing that we can do very well, and this is where it's interesting how particle physics and cosmology get together, because an early universe was very simple. It was very simple and was like I'm not sure if the nuclear reactor is the best analogy, but something like a nuclear reactor or a particle accelerator. So we can actually use fairly simple formulas to predict the distribution of different chemical elements, specifically hydrogen, helium, and lithium. And you can then look in the sky, through a telescope, and you can observe the abundances of hydrogen, helium, and lithium, and you can say, wow, actually it matches with extreme precision to our models. So again, our understanding of the Big Bang is based on the kinds of very accurate measurements that we can do right now. Now notice also, you cannot really fly to most objects in the universe and take their chemical compositions. So the way we estimate the abundances of hydrogen, helium, and lithium is actually by looking at the spectra of light. Absorption and emission of light, of photons of different wavelengths. And you could say, well, does this, can you go and double check, make sure that absorption and emission lines fit what we do here on Earth? And the answer is no. And this is why you have to understand physical theories are not straightforwardly falsifiable. So like this story of the Big Bang, it's not like you can do an experiment and say it's true or it's false. No. You have all sorts of different observations that have to do with distribution of galaxies, observations of photons in the cosmic microwave background, chemical composition of the universe, and once you take them all together, you can see that you take evidence from different venues, and they all fit together beautifully. And this is why we feel entitled to talk about Big Bang with Big Bang story with such degree of confidence. And again, I want you to know, I want to note that it's interesting how our Big Bang model actually play very well with our understanding of standard model of particle physics, basically quantum mechanics, right? So even, and should I talk? Well, I'm not sure if I should talk about this for too long. We do not have a full theory of quantum gravity. And that's the problem. Because we do not have the theory of quantum gravity, we cannot say what was happening at this very early stage. But we have an effective theory of quantum gravity. We know how quantum mechanics works with gravity, how quantum mechanics works with general relativity in certain regimes. Basically, when the gravity is weak and when the distances, the scales are large. We know how these work. The problem is that once you get to scales where quantum mechanics when gravity is very strong and sizes are very tiny at the same time, like in the Big Bang or in the center of the black hole, or inside the black hole, right? This is where our theories break down. And there's regime of applicability. Okay, so I don't know. You see, usually in the lectures, I try to not go into these weeds So, but you see, the only way to understand is to try to explain to other people. This is why I'm doing these videos. But you can hear me struggle because I'm not an expert on this stuff. But you know, I'm trying to understand to some extent, right? So let's talk about. Well, actually, you know what? Let's talk about before the Big Bang. Before the Big Bang, right? And this is where philosophy kicks in, because this is not really a scientific question. Well, it's less of a scientific question. It's not amenable to direct tests and observations. So it's more of educated guesses, and you can have different models of the Big Bang. So the simplest model is that the Big Bang literally is the beginning of the entire universe. It's the beginning. But you have to understand, people find, some people like that. Some people find that displeasing, for maybe for aesthetic reasons or just in general. And you could ask, well, but could it be that there was something before the Big Bang? And you have all sorts of stories. So one of them that is recently in the news is Conformal Cyclic Cosmology by Penrose. And what Penrose basically says is you have these cycles. There's the Big Bang, and then the patch, your observable patch of the universe, reaches heat death, maximum entropy. And then through this conformal transformation, well, Penrose explains in simple terms. He says photons don't experience time, so you can perform a conformal transformation such that the heat death of the previous universe in a different time scale, in a different rescaling of time, becomes the Big Bang of the next universe. And you have these cycles that repeat themselves over and over and over again. And so the story of the universe then would extend into infinity into the past and into infinity into the future. And the Big Bang is more or less a horizon, although Penrose says that maybe you can see the remnants of supermassive black holes in the cosmic microwave background. So maybe there are certain very, very faint traces of the previous, he calls them eons, in the cosmic microwave background. So it could be that the universe is actually infinite. Another way in which you can get an infinite universe, so an infinite universe is infinite inflation. So the idea of inflation gets thrown around. I'm not sure, again, if I should talk about this in detail because this gets technical very fast, but there's I think it's called the horizon problem, the notion that the universe is very smooth and anisotropic. But the problem is the different patches of the observable universe, if our models are correct, did not have time to talk to each other very shortly after the Big Bang. So there was no time for them to sort of, it's like, if you take a cup of coffee, hot coffee, and this is obviously an example due to Sean Carroll, and you pour hot milk into the coffee, or cold cream into hot coffee, they reach thermal equilibrium. They equilibrate, right? And the problem is that within our cosmology right now, in a straightforward sense, there's no time, there's not enough, well, it's like you cannot go faster than light, so there's no opportunity for different parts of the universe to talk to each other and to equilibrate. And so people invented this idea, Alan Guth invented this idea of inflation. I'm not sure if infinite inflation is by Guth. This is an extension of Guth's idea, right? And the notion would be that what happens is the universe is first super tiny, such that there's you don't have to go faster than light. Like everything can equilibrate in this small patch, and then you turn on this process of very rapid expansion, and then you turn it off. It's a hack. It's a hypothesis. We don't know. We have never, and the word that gets used is inflaton field. So the idea is that there was this inflaton field that got turned on and then turned off. We have not observed this. This is purely theoretical. This is speculation. But one of the extensions of this idea is that maybe what happens is like you have something like a lava lamp, right? So you have this inflation going on, And then inflation stops in certain patches of the universe, but continues in other patches of the universe. And so what you get is these like bubble baby universes getting created over and over and over again. So the idea is that the Big Bang that we observe was the local beginning of our patch of space, but actually beyond in time, beyond that beyond that beginning, beyond this Big Bang that we observe, there's actually, again, projecting into infinity, into the past, there's this process of, nucleation, branching, or something like that. Universes, infinite, potentially infinite number of universes being created. And this could actually give you a cosmological multiverse, right? That there are different universes in different places, separated beyond horizons. Again, you cannot travel faster than the speed of light. So beyond the horizon of our observable universe, maybe there are other universes, and maybe these universes have different laws of physics. This is a very interesting idea because it has to do with cosmological natural selection. This gets into the problem of fine-tuning. And there's a word, scape. Well, anyway, so like these multiverses have a landscape of the different laws of physics or of the different constants of nature. And so you get natural selection, some kind of, well, let's say observer selection, observer. This is a very complicated, this is a very important idea, and maybe I should do a separate video on this. But again, in our models, we have to put all sorts of things in by hand, and you have free parameters that you have to fix by hand. And once you do that, it's possible to come and ask, yeah, but why do you have these parameters and not other parameters? And if you change parameters just by a tiny little bit, life as we know it would be impossible. Well, of course, whenever we say life as we know it would be impossible, who knows? Maybe life as we don't know it, hypothetically different life would be possible. But if that were true, you have a problem, because the universe seems fine-tuned, and you get into this problem of God of the gaps, etc. And one potential solution to this problem is, again, observer selection, that you have this landscape of different parameters in the universe, and some of them do not allow for life, and therefore do not allow for observers, and therefore there are no observers there. So you find yourself in a very special patch of space, not because there's something special about you, but because that's the only place where you could have found yourself, right? So it's like we find ourselves on a moderately, not too hot, not too cold planet around this, I mean, what I'm driving at is that like planets like Earth are in the minority in the universe, in the observable universe. Planets like Earth are in a minority. But it shouldn't, if we understand physics and chemistry and biology well enough, we shouldn't be surprised that we find ourselves here and not elsewhere, because life is just impossible elsewhere. Like, life is impossible, as far as we can tell, in the middle of the star, or, on Venus, or let's say on a comet or an asteroid. We should be humble, I think, when we say things, impossible. Sean Carroll gives this wonderful example about microscopic life on the surface of neutron stars. We don't know whether that's possible, but you never say never. So who knows? Maybe it's possible that you have life, different kind of life. But anyway, but you understand, this is the idea that Darwin. Well, it's an idea that's inspired by Darwin. So natural selection produces all sorts of random variation, and then certain traits which are fit to the environment, they get selected for. So kind of in a similar fashion, you produce all sorts of different observable different universes, baby pocket universes within the multiverse. And then life emerges only in those where it's possible to emerge, for life to emerge. Maybe it's 1% of all the universes that exist. Or maybe it's less than 1%. Maybe it's 1/10000000 of a percent. But it doesn't matter, because as long as you have enough universes, enough space, life will emerge somewhere. It's like, if you take, 10 dice, 10 dice, and you just keep rolling them forever, after several thousand tries, or I don't know, you can do the calculation, a certain number of tries, you are bound, you are overwhelmingly likely to get some interesting arrangement. Like 10 dice all show 6s or all show 1s. You just need to have enough time. And this is what kind of infinite inflation gives you. So there are other interesting models, and Carroll, well, it's a model which is due to Sean Carroll, but other people have similar models. You can imagine, because, so get into this very interesting question. We talked about this last time. Are space and time fundamental? Are space and time fundamental? And the answer is not necessarily. And different physicists have different ideas about this. Classically, physicists like Newton just assume that there's a background of space and time, which is changeless and eternal. It's kind of a universal reference frame. But today, many physicists imagine that maybe you can make space and time emerge from something more fundamental. So one idea about time is that actually at the fundamental level, like on the level of this formula, there is no time. There's just a mathematical regularity, and time runs forwards and backwards equally. Time is just a parameter, but there's no preferred direction of time. And the direction of time emerges only because of entropy. And it's a whole separate story. Again, I could do maybe a separate video on this. I don't know. Sean Carroll, this is his favorite topic. He explains this, I think, very well. It's a theoretical idea. We're not sure. Some physicists think that maybe time is fundamental. Sean Carroll doesn't think so. Well, many physicists like Sean Carroll don't think so. And they would say that time emerges from increase of entropy. But what this would mean is that entropy, or disorderliness or chaos of the universe, was extremely low at some early point in the history of the universe. And this seems finely tuned. So entropy gives you arrow of time. And so one solution to this, and this is kind of, again, Stephen Wolfram talks about this a lot. He talks about how many features of the universe you observe maybe because of the kind of observer you are, right? So in this sense, again, we perceive time not because the universe has time, but because we are certain kinds of agents. We are certain kinds of physical systems that experience time. And let me try to flesh out this idea. So what Carroll has, he has a model that just somehow you take this landscape. Think of the multiverse. Take this huge landscape of space and time. And space-time would be one single continuum. And in this landscape, for whichever reason, maybe it's a quantum fluctuation, you get a point of unusually low density. Sorry, a point of unusually low entropy. And so you would imagine that sort of what happens from this landscape is you have two arrows of time pointing in two different directions from this one point. So sometimes I think it's called maybe Janus point. It's like two faces, right? So bidirectional time. This is a way of I don't want to say explaining fine-tuning away completely, but this is one philosophical way to try to give an explanation of what happens before the Big Bang. So the idea is basically if you go back far enough in time. So for Penrose, you get a previous universe, but within this model by Sean Carroll, other physicists have proposed similar models. So Carroll just has one particular model, but there are many like these. What happens is you run into another universe which runs backwards in time from our perspective. I don't know. Is this helpful? Is this useful? Does this make your head ache? Again, usually I don't talk about this stuff in the lectures. This is why I'm so happy that I have this YouTube channel, because I can talk about these things, and if people are bored, they can just switch it off. I'm not imposing this on anybody. Again, so I suppose one reason for me to talk about this is that when I was in my first year, I talked to my friends, and one of my classmates said, no, the Big Bang is just the beginning. There's no other way. And kind of all of these models of bouncing or whatever, they don't work, they never work. And my classmate was just wrong, because they didn't read enough physics. And kind of I'm giving you different models of cosmology within which our observable patch is embedded. And as far as I understand, all of these models are compatible with Lambda-CDM and plus standard model of particle physics. So these would be larger frameworks within which you can inscribe Lambda-CDM. And again, it's like, likewise, if you think of rewinding clock, not in the past, but imagining what's going to happen in the future, in some models, you just straightforwardly get heat death of the universe, and that's the end. So the universe has a beginning, and the universe could have an end. But for Penrose, no. If you wait long enough, there's going to be another Big Bang. In infinite inflation, the heat death is the real end of your patch of observable universe, but there's going to be other universes. And in fact, there are going to be other universes. And in fact, given enough time, it could be that you could have another universe colliding into your patch, which has reached heat death. So, kind of, you could say, should I make this another slide? So, after the heat death. So maybe the heat death is just the end. For Penrose, it's going to infinitely repeat itself. In infinite inflation, it's really the end, but it's the end of our patch. It's local end. For Carroll, with his bidirectional time, there's in some, well, it's like, you understand, you have this interesting point in the past, but in the future, so past is finite, but the future is infinite. And you can imagine all sorts of combinations like these. So again, it's like, one reason for me to talk about this is that I want you to appreciate the complexity. I'm sure I'm not explaining this very well, but I want you to appreciate the complexity and the fact that we have all of these options on the table, and don't let physicists tell you that, oh no, we have figured it out. We don't. And it's like, when people come and they tell me, well, but there's this book written by, Bronze Age desert wanderers that has it all figured out, I get upset, because these are genuine questions, important questions, which have philosophical implications, have moral and ethical implications, and we do not know the answers. And if you tell me, well, no, actually, I spoke to a genie in a lamp and he told me the answer, I get upset. It's not a logical argument. I don't have a logical counter argument to that. It's an emotional thing on my part, and I recognize that, right? It's a limitation. Full disclosure. I don't want to get controversial. I don't want to get conflictual over this point. But I think that when you appreciate the complexity, you get a certain different perspective on things. Yeah. So, do I want to talk? Well, I need to say at least, I'm not sure how long this has been going, but I promised quantum mechanics, so I need to talk about quantum mechanics at least a little bit. Maybe I should have begun with this, because I feel that maybe I understand quantum mechanics slightly better than cosmology. Mechanics, I cannot spell. But basically, I feel that, anyway. So one immediate question, and this is something that we have been walking around a little bit, is determinism. And again, in the story that I have been talking about, I mean, this is a deterministic story. This is a deterministic story. Within, again, Lambda-CDM and, again, standard model of particle physics, once you get to quantum mechanics, people have questions. And it's important to understand, like, in a similar fashion, how you have different models of cosmology, you have different models of quantum mechanics. Well, okay, maybe I should mention. So there are frameworks for Lambda-CDM. So these would be like larger contexts in which Lambda-CDM exists. And, CCC by Penrose, and infinite inflation, etc. So these would be examples of frameworks for Lambda-CDM. But you also could have alternatives for Lambda-CDM. And the alternatives would be, for example, modified Newtonian dynamics. Has to do with the rotation curves of galaxies. Again, we look at galaxies, they don't behave exactly in the way that we want them to behave. So there's a possibility that maybe Einstein was wrong. So Mond basically says Einstein was wrong, and there's a different equation for gravity. But we don't know at this stage. I mean, again, the consensus of the field is that probably Lambda-CDM is correct, but it's a bit early to tell. Now, again, before getting to quantum mechanics again, let me just note, because I want to finish this. Actually, with our Lambda-CDM only accounts for, so I'm trying to say too many things at the same time. So like 95% of the observable universe, we don't understand. We don't understand. So this is specifically has to do with motion. Motion or gravity. So there's too much local gravity. And so in order to explain this, we talk about dark matter. And there's not enough global gravity. So gravity between galaxies. So this would be within galaxies. And this is going to be between galaxies. In fact, again, you have this some like repulsive gravity. So you have this energy that pushes things apart, negative density. So not enough global gravity, and this is what we call dark energy. And honestly, the reason why we call them dark is because we have guesses, but we don't have anything like a solid idea of what this is. And I have spoken about this in the past. Again, remind me sometime. I'll talk about this, dark matter candidates like WIMPs or machos, or dark energy candidates like the vacuum energy of the quantum fields. We'll get there at some point. But I just, 95% of the observable universe we do not understand. And that's cause for some humility, right? So whenever my Humean, whenever we discuss Hume, and we say, well, does induction work? So the fact that the laws of physics have worked in the past, the fact that water nourishes, am I entitled to continue believing in that? No. Again, we'll get to quantum mechanics in a second, but you have this possibility that the Higgs field, which plays an important role in giving particles mass. Mass, I think, is mostly due to energy. Well, I think all mass is ultimately due to energy, but a good chunk of the mass of normal matter comes from the Higgs mechanism. And it's possible, and so the Higgs field has a non-zero value in every point in space. And it could be, in principle, that this is because the Higgs field is in a false vacuum. And what could happen, like this is unknown unknowns, we're not sure, right? What could happen, in principle, there's no way to rule this out presently, is that maybe the Higgs field is in a state of a false vacuum. So it's like if you imagine a ball on a hill, and there's a valley. And so like the ball is on a hill stationary, but if there's a perturbation, the ball can start rolling down the hill. So it's kind of similar kind of picture. So the Higgs field is locally stable, but in fact there's a lower energy potential, because this is what particles do. They seek lower energy states. This formula, it's a Lagrangian. It's an optimization problem. You're trying to minimize action. It's principle of least action. So if the Higgs field could, let's say, quantum tunnel to this lower value, then this would be like a phase transition throughout the universe, which would propagate at the speed of light and would break the normal laws of physics to which we're used everywhere. Again, and this phase transition would propagate at the speed of light, and it could be that it's already moving towards us at the speed of light, and we just have no way of knowing this. And in the next second, or in the next second, or in the next second, like all normal matter will be torn to shreds. It's like, it's like, physicists, feel free to chime in. I think like if the Higgs field, if it's in a false vacuum, certainly normal atoms would be impossible. It's like atoms would not be, electrons would not be able to stick to protons in a normal way. And I think that protons maybe would not be stable anymore. So so this is my go-to chart. So the Higgs field This is the model of interactions in the standard model of particle physics. So the Higgs field couples to quarks, and so it couples to quarks, but it doesn't couple to gluons. So mass of the quarks to some extent, not complete, but to some extent, is determined by the Higgs mechanism. So stable protons would be impossible. Anyway, let me go back. So whole separate story, but kind of, I don't know. It's like string theory, which is string theory is a whole separate thing onto the left field. But string theorists have problems solving their equations in 10 spatial dimensions, and people tell me that an ancient book like Rig Veda has it all figured out. I'm not dismissing Rig Veda. I think it's a very interesting read, but you should not expect it to have all the answers to all the questions. Anyway, let me talk about quantum mechanics. Because again, it's in the title, so I promise. So I gotta say at least some words. Quantum mechanics is a pet peeve of mine. So it's a hobby horse. I love talking about quantum mechanics. I'm not an expert, but I have some things to say. I have some thoughts. So one immediate thing is determinism, because all sorts of people have this misconception that quantum mechanics proves that determinism is false. It's not true. It's not true. Now, what happens is that as a matter of observation, there's observed unpredictability. But the question is, why is there observed unpredictability? Is it the case that it's because there's fundamental randomness, or it's just an observation effect? Like, our uncertainty comes from the fact that our observations are not precise enough. Observational imprecision. And the short answer is we don't know. We don't know. We do not know whether the universe is at bottom deterministic or indeterministic. Now, it's very important that even if there is an element of fundamental randomness in quantum mechanics, it doesn't mean that anything goes, because certain things just never happen. So, for example, there's conservation of charge, electric charge. So an electron is a negatively charged particle, right? You never see an electron spontaneously change charge. Like, this doesn't happen, never ever happens. We have never observed this. There's no reason to suspect that it should happen, right? And we have overwhelming reasons to believe that this never happens, right? So even if universe is random, some things just don't happen ever. So you can have certain interesting transition within the Feynman diagram, and let's say you can have an electron and a positron get together and annihilate. You can have a transformation, but like on its own, I mean, like, but in this transformation, the charge is conserved. And it's kind of interesting because, again, it's a thought that goes back to Thales, to Heraclitus, that there is change, but there's also stability in the universe, and change is according to rules. And another interesting corollary of this, well, I don't know. I don't want to talk about everything at the same time. Anyway, so, but what I'm driving at is that we do not have the final formulation of quantum mechanics. First of all, quantum mechanics doesn't play well with general relativity, so we do not know. So quantum mechanics versus general relativity, it doesn't play well together, so we do not know. And the question is, which one is fundamental? Which one is going to give way? Some physicists think that general relativity is fundamental. Some think that quantum mechanics is fundamental. Or maybe there's going to be a different theory that just... So it's like we shouldn't get too cocky and say, oh, quantum mechanics proves that the universe is random, because, we don't understand quantum mechanics all that well at the end of the day. But then also there are problems of interpretation. And you can have indeterministic interpretation, like interpretations which, like indeterministic interpretation. Like, for example, Copenhagen interpretation or GRW interpretation. Feel free to look this up. So in these interpretations, there's real, genuine randomness, indeterminacy. But you could also have deterministic interpretations. And the two that get most traction these days is Everettian many worlds, This is Sean Carroll's favorite interpretation, and he's one of the apostles of this interpretation. Or another one, which it's like over the years. Well, anyway, the other one is de Broglie-Bohm pilot wave theory. And there are others. So again, Stephen Wolfram has this interesting project of trying to derive math from physics. As far as I remember, his interpretation of quantum mechanics is also deterministic, but it's different. And the problem is that when we talk about interpretations, we mean that all of these interpretations are, at this point in time, they are experimentally indistinguishable. They are now experimentally indistinguishable. So at this stage, we cannot say which one is right. We just don't know. And so it could be that the universe is deterministic, but it could also be that it's indeterministic. And I insist on determinism because I feel it's the simplest, it's the most straightforward, it's the most parsimonious option. It's the option that makes most sense. See, again, like when you throw dice, when you throw a die, you do not know which side is going to come up. And you could say, well, if I knew, the standard idea, this is Laplace's demon. If you were able to know, it's a thought experiment by Pierre-Simon Laplace, a very important physicist in the history of physics. So what Laplace is saying, that if you could know with perfect precision the position and momenta of every particle in the universe, I suppose, and momentum of every particle in the universe, then you would be able to calculate, to predict the future with perfect precision and retrodict the past with perfect precision. To such an intelligence, this Laplace's demon, time does not exist. Because the Laplace's demon can look at any snapshot in time. So any snapshot in time gives you the perfect picture of all the past and all the future. And there is no indeterminism. And again, I talked about this last time. So within general relativity, there's no this relativity of simultaneity. The ordering of events in time is not well defined. It can be different for different observers. So this is not really a knockdown argument for determinism, but this is a circumstantial, tendential evidence in favor of determinism. But ultimately, the reason I go with deterministic interpretations is because they are more parsimonious. They make more sense. It's like if you can, it's what I'm driving at. It's very easy to imagine a universe in which determinism is true, and yet we cannot predict things with infinite precision, simply because our observations are not accurate enough, or maybe there's a methodological reason for why our observations can never be accurate enough. So again, Heisenberg's uncertainty principle. It's unscharfes Prinzip, unsharpness principle, right? That once you look at things which are very, very tiny, you get blurriness, right? But it doesn't mean that the fundamental constituents of the universe are themselves blurry. It may just be that it's a limit of your vision, right? There are certain portions of the universe that we will never see, no matter how powerful our telescopes are, because the speed of light is the cosmic limit of the universe. So outside of this light cone, we cannot see anything. It doesn't matter how powerful your telescopes are. So maybe it's a similar thing. Once you zoom in close enough, there are just certain details that you cannot see, right? And I think it's far easier to explain indeterminacy in this fashion. So actually, when we talk about again this fundamental randomness, I feel it's a very premature and it's a very ambitious doctrine, because it imagines that we already have all the stuff figured out. So we say, let's say, quarks are indeterministic, therefore the universe is indeterministic. But do you know that quarks are fundamental? Are quarks fundamental? Right? So maybe, again, I have this picture over here, right? This is basically the standard model. And this model does not include gravity. So you have to add gravity to this model. This picture is basically a graphical representation of this formula, but it doesn't include gravity. So the idea is that within this model, as far as we can tell, let's say electrons are fundamental. Photons are fundamental. Like, they don't have constituent parts. But how do we know? Maybe there are constituent parts and we just haven't discovered them yet. And in fact, again, there are these hypothetical particles called preons. So maybe once you know, I think this is the way you spell preons. This is the way you spell preons. Once you get to certain very fundamental levels, maybe you can find that randomness emerges from deterministic behavior. Like, randomness emerges from. So I suppose so it's a possibility. So you could say, Alex, but if these are two equal possibilities, why do you go with determinism and not indeterminism? And let me say the following. It's like, what kind of an experiment? So my strong assertion is that it is think about this. What kind of an experiment can you make in order to prove that indeterminacy is true? So you say, I control for all the variables, and I still cannot predict. So what I'm driving at is that methodologically, it is impossible to prove indeterminism, because you'd have to assume that you control for all variables. And if you can't control for all variables, maybe the process is not really random, but there's just a mechanism which you have not discovered yet. So determinism in this sense, well, again, technically speaking, if you think back to David Hume, even determinism cannot be proven, but determinism can work very well. It's like, certain predictions can get very, very good, very accurate, right? And you can be very satisfied that you are able to predict the system with perfect precision. Maybe no guarantees, but there's a certain level of satisfaction. Whereas indeterminism, I feel, is deeply dissatisfactory in this sense, because it's like, again, you're throwing dice. Again, as far as we can tell, on the level of throwing dice, the quantum effects should not really manifest themselves. So it's possible to build machines that will throw dice perfectly each time, and get the result that you want. I'm pretty sure that such machines exist, right? So if you understand, right? So but like what I'm driving at is that dice feel random and unpredictable, but in fact, there might be, it's very easy to imagine, a deterministic process underlying that randomness. But, I should talk about quantum mechanics at greater length, especially these ideas of emergence of space and time from quantum mechanics. And, this particle wave duality. I mean, this is still an unresolved problem. Do you have particles? Do you have waves? I mean, within different formulations, like in Everett's many worlds, the only thing that is real is the wave function of the universe. In the Broglie-Bohm pilot wave theory, you have waves and particles. And particles are real, really real. Some question as to how the Broglie-Bohm should work with quantum field theory, but that's a separate technical issue. Anyway. So, this was actually much more chaotic than yesterday, and this was more chaotic than I expected. But it's difficult for me to talk about this stuff because I'm not a physicist, but I'm trying to draw philosophical conclusions. So anyway, colleagues, I don't know. I hope this was stimulating. If you have any questions by any means about this stuff, feel free to ask them. If you're a physicist and you can correct some of my mistakes, by all means, please feel free to do so as well. Again, I want to say, I understand it's maybe more painful than some of my other lectures, but it's very useful for me to try to explain this stuff. Because unless you, it's like, before you talk to others, you're not sure whether you understand or know yourself. this is definitely not the only thing I plan to talk about. I had a whole host of things. I was planning to talk about Feynman diagrams and string theory and holography, core theory, but this graph from Carroll. But my time estimates are always horrible. Okay, I start the lecture and it's already an hour has passed. So anyway, let me pause here. Again, unfortunately, my schedule these days is completely unpredictable. And I do, incidentally, have a lot of work. So I'm doing this sort of during the breaks before and after. But hopefully this was stimulating, and hopefully this is going to help me do a more coherent pass over all of these topics in September. So thank you for your company. And as always, colleagues, stay safe and take care. If physics gives you a headache, don't worry. I'm gonna get some. Before the end of summer, I'm gonna get some other topics covered. Nietzsche maybe, or Freud. Anyway, see you around.